In this third video on 9.1 counting, we'll cover the last two counting methods, distributions and property of inclusion and exclusion. So distributions is really the same as binomial spellings. So in other words, we're going to use combinations. For instance, how many ways are there to distribute 5 indistinguishable candies? So you can't tell them apart, they all look exactly the same. And we're going to distribute those to 3 distinguishable kids, so we can tell the difference between the kids. How many ways are there to do that? A way to think of this problem is to imagine 2 dividers, which are laid down in such a way as to divide the candy between the 3 kids. Notice we only need 2 dividers. Then one kid gets 1 candy, next kid gets 3, next kid gets 1. Or we can lay the dividers down this way. Rather, this way. I only need 2 dividers, not 3. And so now the first kid gets 2, the second kid gets 3, and the last kid doesn't get any candy at all. So a way to look at this problem is to imagine or to see that you have a total of 7 things. That'd be the 5 candies and the 2 dividers, so 7 things. And we will pick 2 of them to be where the dividers are. So of the 7 things, choose 2 of them to be the dividers. In this case, we're choosing the 3rd thing and the 7th thing. But how many ways can we make that choice of where the 2 dividers go? So that's 7 choose 2, 7 factorial, 5 factorial, 2 factorial. A way that I think about doing this problem without using my calculator is 7 factorial, all the way down to 1, multiplied together, 5 factorial, and you get a lot of cross-canceling when you do that. So I'm imagining that all that's left of the 7 factorial are the numbers above 5 factorial. That'd be the 7 and the 6. And then I'll divide by 2. So it's 42 over 2. So think about the largest number on the bottom canceling most of the numbers on the top and see just what's left of the top. As always, I should be able to list out my sample space to back up my answer, and I should be able to list out my sample space with some kind of strategic way. So I got the 5, 0, 0 group, where each kid ends up with 5, possibly. Then I got the ones with the 4, 1, and 0, with different kid having 4 and 1 and 0. And the 3, 1, 1, and the 3, 2, 0, and the 2, 2, 1, where I can envision a different kid getting the 1. And I get my 21 ways. This problem may look very different, but it's really the exact same problem. How many ways are there to pick an x, y, and z value such that x plus y plus z equals 5? And we're going to work under the assumption that x, y, and z are whole numbers. So this is like the discrete piece of it, that we can't have fractions or decimals. In this case here, x, y, and z are like our 3 kids from before. And there's the 5 total pieces of candy that need to be given to the 3 kids. So for instance, the first letter could get 1, then 2, then 2. That's like the first kid getting 1 piece of candy, the next kid getting 2, the next kid getting 2. Different ways that it could be done. Instead of having 5 candies, we now have 5 single digits, I guess, 5 ones that add up to 5. And I could put my dividers in such a way that the first letter gets this many 1s, the next letter gets 3 1s, so it'll be 3, and the last letter gets 1 1. Again, this is 7 choose 2, and notice that I've even gone to a bit of a shortcut here where I just have 7 for 2 things and 2 for 2 things. The rest of the numerator, which is 5 factorial, got canceled with that 5 factorial part of the denominator. Again, 7 choose 2 is like 7 for 2 and 2 for 2. Here's another question: how many ways to distribute 10 candies to 3 kids if each kid gets at least 2 candies? Now, we've seen this at least wording before. We know that that means a little bit of something special that we have to do. How do we handle it here? And what we're going to do here is, if each kid's going to get at least 2, so let's give each kid 2. Right off the bat, we'll give 2 candies to each of these 3 kids. That's 6 candies. They're off the table. There's only 4 candies left. and we're going to use our two dividers to determine how the remaining 4 candies will be distributed. So we only have 4 candies in contention. The other ones have been given away already, and the 2 dividers. So that's a total of 6 things. Choose 2 of them to be the dividers. 6 times 5, 2 times 1. One thing that maybe you can see in common here is that usually there's a part of the problem that's indistinguishable. The candies, we can't tell the difference between them. They're like the spelling problems where we have 3 E's. Can't tell the difference between them. But who we're giving them to, the kids, we can tell the difference between them. They are distinguishable. So there's a piece of each, distinguishable and indistinguishable. Here are 2 other distribution problems. I'm going to donate $200 to 5 charities in $25 increments. Everybody's going to get at least $25. How many ways can I allocate my money in $25 chunks? And a donut shop has 5 different types of donuts. How many ways can they pack up a box of 12 donuts? So different combinations of the 5 types of donuts. In the first problem, we take our $200 and we give everyone $25 of the 5 different charities because they're going to get at least $25. So let's give it to them right off the bat. There's $75 left, which is 3 $25 increments. So now the 5 charities, we need to put numbers in for A, B, C, D, and E so that it adds up to 3. We could give this one $50, so that's 2 increments. This one $25, that's 1 increment. And everybody else would have to get 0. So I have 5 charities, or 5 kids, and I only need 4 dividers. So basically there's a divider where every plus sign is. So 4 dividers and 5 charities and 3 increments. I mean 3 increments. So we use the number on the side of the equal sign and the number of dividers, and that gets us our total of 7. We can have 7 choose who the 3 charities are who are going to get the $25, or 7 choose where the 4 dividers are going to go. Either way, it's the same thing. With the donut shop, I have 5 types of donuts, and they add up to 12 altogether. So I could pick 2 of this one, 3 of this type, 2 of this type, whatever. I'm going to have, again, 4 dividers to divide between how many of each type of donut is going to be in the box. So in this problem, the types of donuts are like the kids. Instead of how much candy is the first kid going to get, it's how many of the first type of donut is there going to be. And so I have 16 total things. That'll be my 12 donuts and my 4 dividers. And I'm going to say which of the 4 are going to be the dividers of the 16 things. Or I have 16 things, which of the 12 are going to be donuts. The last type of counting that we'll do in section 9.1 is the property of inclusion and exclusion. For instance, I pick a random integer that's somewhere between 1 and 100. How many ways is there for that number to be divisible by 3 or 7? Notice that these are not disjoint sets. So in other words, there's a possibility that the number could be divided by 3 as well as being able to be divided by 7, that it can be in both of these choices. So it is not disjoint sets where it's like it could be a heart or it could be a club. They don't overlap. It's this kind of set here where they're not mutually exclusive, where it could be divisible by 3, it could be divisible by 7, or it could be divisible by 3 as well as 7. We tend to name our 2 groups or sets with capital letters. So like A will be the numbers divisible by 3, B will be the numbers divisible by 7. Here's the notation that we are going to use for this problem. The absolute value, or magnitude, that will mean that we're talking about how many there are when we have the absolute value, magnitude, of A or B. So it's divisible by 3 or divisible by 7. It's anywhere in these 2 circles. We'll add how many are in circle A, and we'll add to how many there are in circle B, but we will have double counted the part in the middle. We will count it both in A and B. So in order to not double count it, I need to subtract it once. So A plus B minus the part that's in A and B. There's the symbol for and, there's the symbol for or. Here's my math work, and I'm using something called the greatest integer function, because to figure out how many numbers from 1 to 100 are divisible by 3, I want to divide 100 by 3, but I don't want the decimal part of that answer. I just want the whole number part. There are 33 numbers that are divisible by 3, from 3 up to 99. Same when I divide by 7, I don't want the decimal part. I just want to know how many whole numbers there are. If it's divided by both, then it's divided by the product of 3 and 7, or 21. There are 4 numbers there, like 21, 42, 63, and 84, that are divisible by 21. And I can add these together. Notice that if I want how many are divisible by 3 or 7, that means it could be divisible by 3, or divisible by 7, or it could be divisible by both. In this problem here, we're going to use also pi, property of inclusion and exclusion. I pick a random integer from 1 to 1,000. How many ways are there for the number to be divisible by 3, 7, or 8? So it could be divisible by 3, it could be divisible by 7, it could be divisible by both 3 and 7, could be divisible by 3 and 8, or all 3 of them. So this would be where the numbers are divisible by 3. This would be the area where it's divisible by 3 and 7. This would be the area right here where it's divisible by all 3, because it's in all 3 circles. Notice that we've never asked 3, 7, and 9, due to the fact that 3 goes into 9. That would be not as good of a question, because really it would just be 7 and 9. So I've drawn a picture here of these 3 sets. Numbers divisible by 3, numbers divisible by 7, numbers divisible by 8. This picture right here is called a Venn diagram. And if I would like to know the magnitude, or how many there are, of A, B, or C, then I could add each of the individual, how many there are that are divisible by 3, how many divisible by 7, how many divisible by 8. That would be all the yellow. But you can clearly see that I have double counted. I've double counted the region that's both A and B, both A and C, and both B and C. So I will subtract out those overlaps. But now let's look at that little region right in the middle. It was counted in A, it was counted in B, counted in C, so it was counted 3 times. And then it was subtracted out for the overlap, for the other overlap, and for the other overlap, so it was subtracted 3 times. So that green area has currently not been added at all. Added 3 times, subtracted 3 times. So for that reason I need to add it back in again so it's counted at least once, and that would be the region that's in A and B and C. Sometimes I might say in this formula we add singly, in other words A, B, C, single letters, subtract doubly, 2 letters, and add triply, all 3 letters together. It's a way of remembering this formula. What if we make a small alteration to the problem and say how many ways are there for the number to not be divisible by 3, 7, or 8? Well, now we'll do complementary counting. There's 1,000 integers altogether, and we'll subtract the ones that are divisible by 3 or 7 or 8 to get what's not divisible by 3 or 7 or 8. So I'd have to do 1,000 minus all of this in parentheses. These are the ones that are, subtract it for 1,000 from 1,000 and get the ones that aren't. In these last 2 problems, we pick a random integer from 1 to 1,000. How many ways would it be divisible by exactly 2 of these numbers 3, 7, and 8? A is 3, B is 7, C is 8. Notice the picture. It can only be divisible by 2 of these, not just 1 of them and not by all 3. And for the second one, at least 2 of these. So it can be by 2, or it can be also by all 3 of them. Notice in the first case, when we count each of the overlaps, we count that yellow section 3 times, so we need to subtract it out 3 times because we don't want to count it. But in the second one, we count that middle section 3 times, but we want to count it once, so we only subtract it out twice.